Hi everyone. So let's do some induction and let's look at some of the problems from the book and some of the examples from the book, at least briefly. So in the first part of chapter 10, the book presents proofs of the following 5 propositions, all by induction. That the sum of, we did this one already, the sum of the first n odd integers is n squared. But they also do the fact that 5 divides n to the 5th minus n, that the sum from 0 to n of I times I factorial is n plus 1 factorial minus 1, that 2 to the n is always less than or equal to 2 to the n plus 1 minus 2 to the n minus 1 minus 1. This one's worth looking at because it proves an inequality, not an equality, by induction. So you should look at that. And here's another proof of an inequality. 1 plus x to the n is always bigger than or equal to 1 plus nx for all x in R with x bigger than minus 1. This one's interesting because it has another variable in it, right? It has an x, which doesn't play a role in the induction, but which you do have to keep track of. You should read and understand all of these proofs thoroughly if you value your survival in this course. I can't put it any more bluntly than that. I'm not going to go through them line by line. They're very carefully explained in the text. But of course, if you have questions about them, then you can ask on Piazza or in the working groups or in office hours. So I already pointed out a couple of things here that are interesting. The fact that number 4 and number 5 prove inequalities and that number 5 has an additional variable. The other small point that I wanted to make is with problem 3, which you'll notice starts at 0. And in the statement of the induction axiom, we had an infinite family of statements indexed by the natural numbers. So we started with p of 1 and p of 2 and so forth. So in fact, the induction axiom says, given a family of statements p of n for n in the natural numbers, if p of 1 is true, and for all n in the natural numbers, p of n implies p of n plus 1, then p of n is true for all n. But what about if you have a family of statements which are labeled that start at 0? So let's compare. So suppose q of n for n in Z, n bigger than or equal to 0, is a family of statements. And suppose if q of 0 is true and q of n implies q of n plus 1 for all n in Z, n bigger than or equal to 0, then all q of n are true. How do we compare these two statements? Well, in fact, they are equivalent, but I'm going to make this into a proposition, and I'm going to prove it using the axiom of induction. And the proof, so here, what's the difference? Here we have p of 1, p of 2, p of 3, and so on. And here we have q of 0, q of 1, q of 2, and so on. How do we connect those two things? Well, let's define p of n to be q of n minus 1. So in other words, for n bigger than or equal to 1, or in other words, n in the natural numbers. So then p of 1 is q of 0, p of 2 is q of 1. So by the hypotheses of our proposition, Q of 0 is true, so P of 1 is true. And also Q of n implies Q of n plus 1. So remember that if P of n is Q of n minus 1, then Q of n is P of n plus 1. But this is true for n bigger than or equal to 0. So we have P of n plus 1, excuse me, implies P of n plus 2, starting at n equals 0. So P of 1 implies P of 2, and so on. So the P's, which are the Q's of n minus 1, satisfy the inductive axiom. So by the axiom of induction, P of n is true for n equals 1, 2, but therefore Q of n, which is P of n plus 1, is true for n equals 0, 1, 2, and so forth, because Q of 0 is P of 1, which is true, and so on. So you can start your induction from 0 if you like, and it's still going to work. And in fact, you can start your induction at -50, and as long as you only go in one direction, you're going to be fine. What you can't do is start at 0 and go in both directions, at least not without more hypotheses. So that was a point that I just wanted to make about problem 3. Once again, read these theorems carefully, make sure you understand their proofs, ask if you have questions. Now I'm going to do a few more proofs by induction just to get a little more practice. The proof is the next one is this proposition that's called the formula for triangular numbers. The reason is because if you look at 1, 2, 3, you make a triangle by stacking up circles. So then you have here 1 plus 2 plus 3 plus 4, which is 10. So 10 is a triangular number. And if you use this formula, 1 plus 2 plus 3 plus 4 is supposed to be 4 squared plus 4 over 2, which is 20 over 2, which is 10. So these are the triangular numbers. And if we want to prove this by induction, let's first work out what the various statements are. So P of 1 is the statement that 1 equals 1 squared plus 1 over 2, which is 2 over 2, which is 1, which is true. P of 2, just for the sake of getting things right, is 1 plus 2 equals 2 squared plus 2 over 2, which is 6 over 2, which is 3, and that's true. So what we must do now is we want to apply induction we must show that P of n implies P of n plus 1 for all n in the natural numbers. And P of n is the statement 1 plus 2 plus n equals n squared plus n over 2. And P of n plus 1 is the statement 1 plus 2 plus n plus 1 equals n plus 1 squared plus n plus 1 over 2. So we have to assume star P of n, and must show star P of n plus 1 follows. And this is a little bit of algebra. Namely, we write 1 plus 2 plus n equals n squared plus n over 2. We add n plus 1 to both sides. And we get n squared plus n over 2 plus n plus 1, which we can put over a common denominator. So it's n squared plus n plus 2n plus 2 over 2, which is n squared plus 3n plus 2. And n squared plus 3n plus 2 is actually equal to n plus 1 squared plus n plus 1. Because this is n squared plus 2n plus 1. I forgot that divided by 2. This is n squared plus 2n plus 1 plus n plus 1, which is n squared plus 3n plus 2. So we've shown that p of 2, p of n plus 1, is a consequence of p of n. So the formula holds for all n in the natural numbers. Next, I want to prove a useful fact about what are called geometric series, or you can think of it as a polynomial identity. You already know some of these examples. So this is a claim about polynomials. If n is 1, this says that 1 plus x equals x squared minus 1 over x minus 1, which is true, right? Because x squared minus 1 is x plus 1 times x minus 1. And if n is 2, this says that 1 plus x squared is x cubed minus 1 over x minus 1. And in other words, that x cubed minus 1 is x minus 1 times x squared plus x plus 1. And maybe you remember that from calculus. So this is the generalization. It's the finite geometric series. So p of 1, we already checked, is the claim that 1 plus x equals x squared minus 1 over x minus 1. And that is true. P of n is this statement that 1 plus x plus x to the n is x to the n plus 1 minus 1 over x minus 1. And p of n plus 1 is 1 plus x plus x to the n plus 1. And that's supposed to equal x to the n plus 2 minus 1 over x minus 1. And we want to show that p of n implies p of n plus 1. So we assume 1 plus x to the n is x to the n plus 1 minus 1 over x minus 1. We add x to the n plus 1 to both sides. Then we put the right-hand side over a common denominator. And you notice that we have a plus x to the n plus 1 and a minus x to the n plus 1. They cancel out. And sure enough, you get x to the n plus 2 minus 1 over x minus 1. And this together with this is, here we've assumed this is p of n, and we've shown p of n plus 1. So the formula holds for all n by induction. And now let's do one which is a little bit different. It's a statement about sets. So it says, suppose you have some universal set. Here it is. There's U. And then you have a bunch of sets inside the universal sets. Here they are. And it's saying that if you, maybe I will put 3 of them. And it's saying that if you take the intersection of all of them, which in this case is here, and you take its complement, which means, maybe I need a better, try again. So this is the region that we're interested, this is the intersect, so here's A1, A2, A3, and this right here is A1 intersect A2 intersect A3. If you take the complement of that set, that's in green, that's everything out here. The claim is that this is supposed to equal the union, it's supposed to equal A1 complement, union A2 complement, union A3 complement. And that this is supposed to be true for an arbitrary number of sets. A problem because we have this n in there. And you notice here that n is bigger than or equal to 2. And remember, I remarked you can start at 2 and then go on upward. And the axiom of induction in that case becomes, so let's first say, what is P of 2? P of 2 is the statement that A1 intersect A2 complement is A1 complement union A2 complement. P of 3 would be A1 intersect A2 intersect A3 complement is A1 complement union A2 complement union A3 complement, and so on. So to prove this by induction, we need to check that our first case, which in this case is the case where we have 2 sets, P of 2, is P of 2 true? Is it the case that A1 intersect A2 complement is A1 complement union A2 complement? Well, the set of elements in X is in A1 intersect A2 complement means what? That it's X is not in A1 intersect A2, which means that either, this is an and, to not be in the intersection means if you're not in A1 intersect A2, you're either not in A1 or you're not in A2. And that's the same thing as saying that you are not in A1. I mean, it's the same thing as saying that you're either in the complement of A1 or the complement of A2. So the case P of 2 is true. Now we assume that this is true if you have n sets. And what happens if you stick an an plus 1 into here? Well, then you need to know that show that A1 intersect A2 intersect an plus 1 complement is equal to A1 complement union A2 complement union an complement. So how can you get a grip on this? Well, one way to do that is to call, let's let, for the moment, X be the set A1 intersect A2 intersect an. So that the right-hand side here is X intersect an plus 1 complemented. But by the statement for 2 sets, this is actually, we know this is equal to the complement of X union the complement of an plus 1. And the complement of x is equal to a1 complement union an complement because that is p of n. So this here is p of n. I forgot an plus 1 here. This is p of n plus 1. And x bar, which is the complement of an intersection of n sets, is the union of the complements of those n sets. That's exactly what the assumption is. That's what p of n is. So therefore, this right-hand side here is a1 bar union an bar union an plus 1 bar. And now we've shown right here p of n plus 1. So we've shown that if you can do the calculation with n sets, and n is at least 2, then you can do the set calculation for n plus 1 set. Notice though that we needed to know this for 2 sets. It wasn't enough. Doesn't make any sense for 1 set. Okay, that'll give you something to ponder. Think about that and take a look at some of the problems at the end of in the various sections in Chapter 10.